Hi everyone, and welcome to today's webinar, which is the Advanced Modelling Features of LimitState Ring. It's the fifth of our regular webinars that discusses the use and the features of LimitState products. My name is Tom Pritchard, and shortly I'll be passing you over to our speaker for today, who is Matthew Gilbert. The session should provide you with an insight into some of the less well-known features of our masonry arch analysis software LimitState Ring, such as how to diagnose cracks in bridges and how to identify potential load paths under service loads, and also a number of other features. The main section of the webinar will run for about 35 to 40 minutes, and there'll be some time at the end for questions, which you can post at any time via the question functionality that's present in the interface on your screens. As always, we do try to answer as many questions as we can during the webinar, but sometimes time doesn't allow it, so apologies in advance if we're unable to get round to your question. We will, however, follow up on any unanswered questions after the webinar is finished, and if it does spark any questions later on, then you're always welcome to contact us on info@limitstate.com, and we'll be more than happy to answer these in detail for you. So, without further delay, our speaker for today is Professor Matthew Gilbert, and he's the LimitState Ring Product Manager.
Thanks very much, Tom, and thanks very much, everyone, for joining us for the webinar today. Okay, so the first opening slide just gives you an indication of the sorts of structures that we are going to be considering during the webinar. So multi-span structures, for example, with a variety of different loading regimes. And in the bottom image, you can see a multi-ring brickwork arch bridge where actually we've modelled the ring separately, so we can model what's commonly called ring separation and the effect that might have on the response of the structure. In terms of the webinar, this gives you a little rundown of what we're going to cover. First of all, say a very few words about LimitState, and then move into the background to the main subject matter, so masonry arch bridges and how we go about analysing those. Then move on to the meat of the webinar, looking at the advanced modelling features. Three in particular we've picked out. One is use of the support movement mode. Secondly is modelling specific defects in a bridge. And lastly, briefly looking at how we can model discrete reinforcement. Then wrap up with conclusions and questions. So first of all, just a few words about LimitState. We're here to provide engineers with software primarily focusing on ultimate limit state behaviour, although that is an evolving process, and we're broadening our outlook in that sense as we speak. We make use of optimization technology that's not used by normal or more standard software vendors, and we provide software which is validated and robust, hopefully. And finally, software is fully supported by our small team here in Sheffield, UK. So if you have any problems, you can contact the support team. We've got users in more than 30 countries worldwide, and they include some of the largest engineering consultants and contractors out there. In terms of where we fit, lots and lots of tools out there to analyse engineering structures of various different sorts. I think you could categorise them as being sort of hand calculations, sort of traditional hand calculations of the sort you find in textbooks, which we might automate in a spreadsheet or in a simple software application. So that's on the left-hand side of the screen there. And what's happened in the last 20, 30 years is that advanced tools based on, for example, nonlinear finite elements or discrete elements have grown in popularity, and those are available for use as well. The downside of the former, the traditional tools, is they have very limited application, so you keep trying to apply them to problems which is really beyond their remit. On the other hand, the advanced tools can be applied to arbitrary problems, but the investment of time, operator expertise and so forth is large. So we try and push a mainstream alternative to those two based on numerical rigid plastic analysis. And so the idea is that you don't take any more time than you would using traditional tools, but you have much of the flexibility of the advanced tools. And we are applying this kind of methodology not just for masonry arch bridges, but also other structures such as concrete slabs, geotechnical constructions. Moving on to today's webinar, obviously we're interested in masonry arch bridges. We know there are a lot of them around there, so 40 to 50% of the bridges on railways in UK and in Western Europe are masonry. They're almost all now more than 100 years old, and we subject those to often increasingly heavy loads, certainly if we're thinking of the railways. The other thing to say is that they're all tend to be unique, so they have unique construction details, and also they can have unique defects or damage caused by a lifetime of being on this planet, but also being subjected to a specific regime of loading and or support movements. What's LimitState Ring? Well, it's interactive software that we use for investigating the stability of masonry bridges. We can apply it to single multispans, and we can identify a wide range of potential failure modes. We can also model localized properties and defects, support movements, and the effects of reinforcement. And these last 3 bullet points are the real focus of today's webinar. I think it's important to just say a few words about how the software works, even though this is primarily focusing on advanced modelling features. So if you choose probably the simplest structure you can imagine, it's a single span masonry arch vault, so there's actually no soil around here. What we do is we discretize that arch into rigid blocks, and what we do to find a solution is we look at all the possible equilibrium states, which we can visualize as lines of thrust that fit within the arch geometry. And we know, because it's a statically indeterminate structure, that there are many of these. But of all these, we use optimization to find the one that corresponds to the maximum load factor when using the software in normal mode. So for example, if we have a quarter span load, we effectively try to find what the value of load needed to cause effectively this structure to transform itself into a mechanism, which coincides with the point where we can only just fit that line of thrust within the masonry. So we can model hinging mechanisms, but we can also model sliding mechanisms as well, and combined sliding hinging mechanisms in a completely arbitrary way. Now you may say, well, how do we do that? In terms of the mathematics, it's actually quite straightforward, although you may be daunted by the sort of unfamiliar equations. But basically what we're doing is we're looking at each and every one of the blocks that makes up our construction. So we've got one highlighted in the green ellipse. We basically look at equilibrium of that block. So we say basically in the vertical, horizontal and rotational sense, those forces or moments have got to sum to 0. We also look at the contacts that lie between the blocks. So I've highlighted one in red. And for each and every one of those contacts, we check that the yield condition is satisfied. When I say yield in the context of masonry, I mean frictional sliding, and also rocking, and also combined rocking and crushing of the masonry. We've actually just got pure rocking and pure sliding for sake of simplicity shown on this particular slide. But the key thing is the statement at the bottom there. This boils down to a linear optimization problem, which is easy to solve. So the normal usage mode of the software is to try to work out what the ultimate limit state or collapse limit state of the structure is. At that point, we have a single line of thrust or equilibrium state, which we can easily calculate using limit state ring, as we've seen. However, in service load scenarios, there are lots of possible lines of thrust. And what we can do, however, is we can use support movement mode to move the supports in a given pattern, which gives then rise to a unique line of thrust, and we can then traverse vehicles, for example, across the structure to try to see what effect those vehicles have on the equilibrium state or line of thrust in the structure. Now, what I've talked about so far has been very simplified because it's been couched in the terms of masonry, so masonry blocks. In reality, a masonry bridge comprises not just masonry blocks but also surrounding material, typically soil backfill material. That soil backfill material does three things. It pre-stresses the masonry in the arch barrel, so it makes it more difficult to disturb effectively. Secondly, we have dispersion of whatever vehicle load we have on the bridge, so that by the time that load reaches the masonry, it's actually more spread out, which is normally beneficial. And then lastly, as we sway into the surrounding fill material, we have passive type restraint coming into play. And the way we model that in limit state ring is using what we call backfill elements. And these backfill elements, so one-dimensional elements, which are active or mobilized if the masonry is moving into them, and not mobilized if the masonry moves away. And so what we're saying is we're modeling passive resistance. We're actually ignoring active pressures, which are typically relatively small. And the slide shown here just gives you an indication of all these different entities. The other thing that you can see here is actually we're not dealing with a line of thrust, we're actually dealing with a zone of thrust, where the thickness of this blue line representing that zone of thrust is a function of the thickness of masonry required to carry the particular load. I won't go into this in any detail, but we actually developed the software, or I was personally involved in developing the software some 25 years or so ago, using it to understand the response from laboratory tests. And you can find some of that very early work in papers in the Structural Engineer Journal in the 1990s. More recently, we've done both small and medium-scale tests. So, for example, we have some very, very simple small-scale tests shown on screen now, where we're actually trying to decouple some of those effects of the soil in order to understand whether the model that we have in the software is sensible. And in fact, we found that it was, and we were within 10% of the predicted capacity in each and every one of these tests. And medium-scale tests, building bridges in effectively large fish tanks. And that work has been going on for some 10 years or so. And it allows us to properly understand how a masonry arch barrel and surrounding soil interact with each other. Okay, so moving on to the advanced modelling features. What I'm going to do is go through each of those three areas that I mentioned at the start. The first of these is looking at identifying load paths and the causes of cracks. And what I'm going to use to help me is the support movement mode in limit state ring. So support movement mode will actually do both of those things, understand how a structure carries working loads potentially, and also diagnose the likely causes of cracks. Just before I get on to an example, I'll just, for sort of completeness, show a slide which shows how the formulation is changed to deal with that. Actually, it's changed in a very, very minor way. Instead of maximising a load factor, we're minimising energy done by the supports, where that is defined as the specified support displacement multiplied by the reaction force. So it's a very, very simple, small change to the formulation. And the example I'm going to use is a simple free-span bridge carrying a heavy goods vehicle, HGV. So I'll move away from the PowerPoint and now move to the software. So this is the software. I've set this up. It took probably no more than 2 or 3 minutes to set up using the Bridge Wizard. What I've got is a series of arches, which are actually using one of the built-in geometries. In this case, the free-centered or pseudo-elliptic built-in geometry. However, what I would say is, in reality, it's normally appropriate to use one of the user-defined shapes using the measured geometry of your structure. And the reason for that is the shape of the masonry in relation to the pattern of loading governs stability. But for sake of simplicity, I've entered this particular shape of arch. If I use the software in normal mode, then what I want to do is to see what multiplier or factor on the applied load, which in this case is this heavy goods vehicle, is going to lead to failure. So what I've got then, when I click the Solve button, is an adequacy factor or multiplier of 3.5, and it's that multiplied by the weight of this vehicle, which I can see the details of. So this is a 40-ton, 5-axle articulated lorry. So multiply of 3.5 on that load is going to cause collapse. And what I can do is I can move the vehicle around, just using the interface to try and find the critical location. And in fact, I was probably pretty close to the critical location at the start, but that's neither here nor there. If I wanted to speed that process up, then I can actually set the software to run the vehicle across the bridge automatically. In terms of the setup of this particular problem, what I've got is clearly 3 spans. I've actually specified backing material above each of the piers, and that is effectively there to represent relatively strong masonry material of the sort that you would typically see in a structure like this. So typically, for this kind of geometry, you would have solid material above the pier head, whether that be concrete or masonry material. This is one way of achieving the solid material. Another way is to actually, you can actually just select using the select functionality and actually select a whole series of contacts, and you can actually glue those contacts together to represent a large chunk of masonry sitting at the pier head. However, this particular webinar isn't primarily about using the software in normal mode. So what I'm going to do is I'm actually going to move the vehicle off the structure. Then the software is a little bit confused. It's now saying the adequacy factor is locked because it can multiply up the load imparted by this vehicle ad infinitum. It's not going to cause any problems. And what I need to do to get meaningful results is move to using the support movement tool. So I click the support movement wizard, and what I can do is I can basically select each of the supports and move them by a given amount. So for example, I could move this left-hand support from right to left by 1. I could then choose another block. Let's suppose each of these spans spreads by 1 millimeter, so in which case I don't need to move, I don't need to touch the first pier base, but the second one I need to move by 1 millimeter. And then the last one, so the abutment, I can move by 2 millimeters. And so now, if I click solve, hopefully I'll get something. I've actually got something that in terms of numerical calculation isn't that meaningful. I get a work. More useful is I get a mode of response. And you can see, hopefully, that I've actually got 3 hinges forming in each of these spans because I've effectively relaxed the spans, or gradually increased the distance between those supports. Okay, so that's interesting. And if I was looking to diagnose the cause of existing cracks, which I'll do shortly, I can try any combination of movements of adjacent supports in order to try to replicate the observed conditions in the field. But in this case, what I'm trying to do is actually replicate what we typically have in a field bridge out there, which is that we have a structure which is effectively sort of shaken down to a statically determinate or near statically determinate form. And the interesting thing now is to go back to my vehicle and actually move that vehicle across the structure. Now, the load imparted by this vehicle is not a factored load, it's just whatever the axle loads that were specified in that table before. So this is a 40-ton vehicle. And we can see how these hinge positions change under the action of this vehicle. And you can see, hopefully, that the hinge positions in the spans do move a little bit, and also the thrust in the pier, the location of that changes, but actually we don't ever get any hinges in the pier. So the key thing to watch out for is where you get very significant changes in the thrust line and potentially opening and closing hinges under the action of service loads. If you have that on a regular basis under standard loading conditions, then that is likely to have a detrimental impact on the long-term sustainability of the structure. So hopefully you can see that we can use this functionality to give us a better understanding of what's likely to be happening under the action of service load conditions. So that's the first sort of usage or use case of the support movement functionality. Another use case is to try and diagnose the cause of existing cracks. So what I'm going to do is I'm going to go to back to the wizard. I'll clear all these, and I'll instead click on the first pier and suppose that, for example, it moves down by 200 millimeters. So it says Y positive is upwards, so I actually want to do minus 200, say, to replicate a 200 millimeter settlement. So I click OK, click solve. Oh, I think I must have clicked the wrong. I think I gave it an X instead of a Y, so I wasn't paying attention. I'm meant to do a vertical displacement. Okay, that's what I wanted. Oh, don't want that much. Okay, so anyway, so you can see now that we have a series of cracks in the adjacent spans caused by a settlement of the pier. And if we wanted to, we could look at that in a different way. We could say, okay, so if I was looking at a bridge, I would be expecting a crack in, for example, in the intrados like that. I'm not going to see the extrados crack. Okay, so actually this is a reasonably close approximation, or rough and ready approximation, of a bridge actually in the field. This is actually Linton Bridge near Leeds, which did suffer a support settlement of around 200 millimetres during the Boxing Day floods in 2015. In this particular case, vegetation is obscuring that first span, but if I go to a close-up, you can actually see that there is a transverse crack in a similar location to what we see in the model. Actually, it's probably a little bit higher up the arch, probably suggesting there's a little bit more backing in this bridge than is present in my model. And what that suggests also is that you can view a settled bridge as an opportunity. So if you have a population of similar bridges, one of those bridges is settled. If you can get a good correlation between your model and the behavior in the field, then your model is probably pretty sound, and then you can apply that model with more confidence to other bridges in that population. And it just shows you the situation above on the road, so you can see the effect of the support movement is pretty clear in terms of the deformation of the road surface and the parapets. Another example, less recent in terms of the date of the settlement, but quite severe nonetheless. And you can see again the line of the parapet as a telltale, and also the shape of the first span is hopefully quite clear. It's quite distorted. Now, this particular bridge is interesting because that support movement occurred quite soon after this bridge was constructed. So it happened in the very early part of the 20th century, and trains have been busily crossing this structure ever since. And until quite recently, detailed calculations trying to understand what had happened and what the performance, what the impact on the performance was, other than observational. Yeah, so that's only been carried out relatively recently. And so what we did, or what a consultant did using the LimitState Ring software, was actually apply settlements in order to replicate the cracks that they saw in practice. And actually it was possible to replicate relatively closely the cracks that you could see in the field. Certainly the significant cracks in the model were clearly evident. Some of the more minor cracks were not so evident. So this can be very useful in getting a better understanding of the structure that you're dealing with. Interestingly, in this case, when you do an analysis using the deformed shape of the structure, the load carrying capacity is not significantly affected, even though the support movements involved are quite significant. So sometimes support movements even though they have quite alarming impact on the shape of the structure, sometimes they're not actually that damaging in terms of the load carrying capacity. Okay, so second example is modelling specific defects in a bridge. So we can model both local and global details, including defects in a structure. The way we do that in the software is we use the property editor at the right-hand side of the viewer. And what I was going to hopefully quickly do is just show this with a very simple example. Around the time we were testing lots of full-scale bridges in the lab, we also tested simpler structures that we could use to calibrate and check the model. So we had, in this case, 4 arch vaults. First one with the rings fully bonded together, second one fully unbonded, and then the third and the fourth one we had partial bonding. And that partial bonding was either via use of steel plates as a retrofit, or just simply using headers that connect the two courses together. So I have go back to the software. I have hopefully an arch all set up. So this is actually the arch 1 effectively. So what I've done is I've actually, although it looks like it's a normal soil fill bridge with a vehicle, we've switched off the effects of that backfill. So there's no self-weight, there's no dispersion, etc. And if we apply that load, then we end up with an adequacy factor which actually has been normalized to give us the load in kilonewtons. So it's actually around 4 kilonewtons here. But what I can do using the software is I can actually split that arch barrel into 2 rings. So instead of having 1 215 thick arch barrel, I'm going to have 2 107.5 rings, and I can solve that one, and you can see straight away the load has gone down from almost 4 down to 1.47, so around 1.5. And you can also see that we have diffused hinges and actually multiple lines of thrust in the arch barrel. So using this ability in the property editor, what I can do is I can actually select contacts where I either had a steel plate connecting these together, or I have a header course between them. So I need to count these up: 1 2 3 4 5 6 7 8 9, and then I have a header, and then I have 1 2 3 4 5 6 7 8 9, and then a header. So what I can do is I can actually change the properties for these contacts only, so that I'm not allowing hinging or sliding. And I now have a slightly different mode of response, and I have actually a much higher capacity than I had previously. So it had gone down to 1.47, around 1.5. It goes up to 3.2. And if I go back to the slides, then this is the one with the headers, and actually you end up with a very similar mode of response to what we see in the model, and also in terms of the load carrying capacity, very, very similar values for the collapse load. Just very quickly look at a structure in the field. This is a short span structure, very short span, arguably not a bridge, a culvert. So we've got the details here. In the survey, we have a loss of connectivity or adhesion in the middle section between the rings. So we have ring separation, and we have intact sections near the abutments. So we can model that and we can model the likely mode of response. We can look at the capacity, and we can also look at potential ways of strengthening that structure. So, for example, we could, put in some mechanical fixing between those rings, bearing in mind that whatever we put in there has got to be stiff enough as well as strong enough to restore the connection between those rings. Okay, which brings me nicely on to the last topic I was going to cover, which is modelling reinforcement. So we can very easily basically augment the contacts with potential reinforcement, whether that be compressive or tensile reinforcement near to the upper or lower surface of the masonry. So what we have, because we have a plastic model, effective rigid plastic model, we assume that the reinforcement yields at a prescribed force in a ductile manner. We neglect the likelihood for debonding, and overall we're hoping or assuming a ductile mode of response. So we're not modelling a brittle failure. So those are caveats, so you need to be very careful when you're applying reinforcement to a masonry structure that you don't trigger an unwelcome brittle mode of response. In terms of validation, TRL tested 2 5-metre span soil-filled bridges some years ago, one with no reinforcement and one with retrofitted reinforcement. The details are given here, so we have a tensile force effectively. I think I've got the I can pull up the model. So TRL unreinforced. If I click solve, then I get this characteristic multi-ring mode of response, and I get actually an adequacy factor or a load carrying capacity in this case close to the experimental value of 200 kilonewtons. What I can do is I can use the contact select tool. I can select all the contacts in, for example, the lower ring. And actually, the first thing I actually need to do actually is go back and say that I'm including reinforcement in order to give me all the options. I'll just retrace my steps there. So select all those contacts. And then if I select the potential for reinforcement, then we can actually put in reinforcement. So I've got 90mm depth. I've got, I think it was 149.3 kilonewtons that could be tensile or could be compressive. I think that's everything. So I can then solve again, and we've got a new adequacy factor, in this case collapse load, and we have also we have a line of thrust which is going to pass outside of the thickness of each of these rings now. So actually we have the capability to plot shear forces and normal forces and moment diagrams, which are a bit more meaningful when you have reinforcement. Okay, so just coming to the end then of what I wanted to cover, so just wrapping up with some conclusions. Hopefully you've seen support movement mode is very helpful in exploring load paths under service loads, and also can be used to look at the likely causes of existing cracks. Sometimes those are obvious, sometimes less so. We can model local defects such as partial ring separation, and we can potentially model reinforcement, but the caveat being that we're assuming ductility, so need to be very careful when you're using that functionality. Okay, so moving then on to last part, which is opportunity for questions. I'm just going to open up the the dialogue. So there is a capability for you to enter questions in the utility that you should see on screen. Just having a look here. Any questions? Just having a look. Okay, so question about effective width. I'm just trying to understand what it. So, how to assume effective width? Okay, I think probably one of the structures that I showed didn't have a very sensible looking effective width. So, if I go back to I think it's this triple span. I actually modelled an effective width of 2.5 meters. That's a fixed width. Now, it is possible in the software to have an auto-calculated effective width using, for example, assessment code stipulation. So, for example, in the UK, we have a Highways Agency assessment code, which specifies various different things about the effective width that you should assume, and it's actually contained here. And what it actually then does is, depending on the location of the vehicle, it will actually change the width that's being modelled. So I don't know if we're going to be able to see that. So it's actually shrinking as I get the vehicle over the crown. And the reason the width is shrinking is because it uses an effective width based on the depth below an axle. And when you've got multiple axles, it uses the minimum depth in the whole model. So hopefully that helps helps the question. I wasn't, the way it was worded, I wasn't 100% certain what was meant. So please add a clarification if I didn't answer that. Then, okay, just looking at. Okay, how would you define brittle failure of the reinforcement? Okay, so I wasn't referring to brittle failure of the reinforcement. I'm assuming that you're using ductile material. The caveat is it's a bit like in reinforced concrete. If you over-reinforce a section, then you actually can end up with actually in that particular case it's a brittle or explosive failure of the concrete section. So you can change the mode of response quite significantly. If you put in relatively small amount of reinforcements, it's lightly reinforced, then you can expect the mode of response to be largely similar to the unreinforced case, but that you have a slight uplift in load carrying capacity. I've got another question here. I'm probably just going to do the last one as we're running low on time. Of the advanced modelling features, which parameters are found to be most sensitive to the capacity? Okay, so the advanced modelling features that we've talked about. So we've talked about reinforcement. So that it's dependent on where you put the reinforcement, how much. We've talked about changing local properties. So, for example, what we could do here is, in a particular model, is we could, for example, model washout of mortar if this bridge is crossing a stream. So we can model that, and the capacity is going to be very sensitive to that if the critical failure mode anyway involves rotation of that hinge. So it's actually quite difficult to generalize which of the parameters is most important. What I would say is the masonry strength is often not that important, particularly when you're dealing with short span bridges, because the stresses involved in those sort of structures are relatively small, so the strength of the masonry in relation to those stresses is typically quite high. What I would say is software like Ring, it allows you to play around and do these kind of what-if scenarios very, very readily. And so you don't need to take my word for it about which parameter is important or not. You can actually try and do a sensitivity response for yourself. I mean, the other thing to say is shape can be very important because it's the shape of the masonry in relation to the pattern of loading which is governing stability. Okay, so I think that's probably all the questions we've got time for. Those of you who've answered questions that we haven't been able to answer, we will answer those by email after the event. I'll hand back over to Tom now.
Thanks, Matthew, and thanks to everybody for listening today. We do hope you found the webinar informative. For those of you who aren't current users of LimitState Ring, we will get in touch with you over the next few days just to get some feedback, find out if you have any further questions, and see whether you think LimitState Ring will be useful. Please also look out for the event notifications that will be sent out via email and also posted on our website at limitstate.com/events. Also, it's worth noting that there's a special offer on purchases of LimitState Ring during July, when we'll be offering 20% off the purchase price. So again, do look out for that on our website and in emails and things that have been going out. So lastly, again, thank you for taking the time to join us today, and we do hope to see you again for one of our future sessions. Goodbye.